Or 2,500. Please, if you want to eat or you want to buy anything, do it now. We are starting in 5 minutes time. All right, let's start. Alright, equilibrium of forces. Equilibrium of forces. Equilibrium of forces. Equilibrium. Please tell your friends to start coming back. We started. Equilibrium of forces. Equilibrium of forces. Now, under this equilibrium of forces, the key concepts we are going to be focusing around under this course is that first we have to know what equilibrium of force is. Have to know what equilibrium of force is. Please. Number two is that we have to know the difference between moments of force. And then the difference between moment of force and moment of force at a point, or we say about an axis. Then the third thing you will need to know under this equilibrium of forces is what we call the torque, or let's classify torque under this. So that we make room for now what we call center of gravity. And then center of. Alright, Tommy. Yes. So under equilibrium of forces, we are going to be centering all our topic and concepts under that key points, under those key points. So equilibrium of forces, moment of force at a point, or about an axis, center of gravity, center of mass. Yes. So please, those of you that maybe you come and you ask me, sir, I was not in class when we did this one, and I said the video, you don't use the video link. Please, why we make all these videos that you see us doing, so that as we learn in class, if we have reason to repeat it, we send the video you were watching. But once they send you that video, some of you want to save data. You are managing data. But you don't have to. Yes. You need to know that you don't have to. You can just start network here. Network here? Yes. Yes. It's a problem, yes. I don't use it to finish. Okay. One thing is right now. Equilibrium of force as a subheading. So right, equilibrium of force is a state where an object experiences no net force. That is one. It is a state where an object experiences no net force. No, we don't like speaking English in physics. So once we speak that English, we need to talk about it. I said it's a state where an object experiences no net force. It is a state where an object experiences no net force. Mary Jasmine, you can't see what? So I said it's a state where an object experiences no net force. Have you written it? Alright. Now see what I mean by that. If, for example, I have this to be a rod, a uniform rod. Let's say this is B, this is B. Notice that if this thing is being, let's say, held by a rope, if it is going to be stable or having static equilibrium, it simply means that this particular part cannot move. This particular part cannot move. So once you have balance, or once an object has balance, that object is said to have equilibrium. So for balance to be achieved, there must be no net force, because if there is a net force acting on this and not acting this way, that means that this object will tend to move downwards. Is that okay? Yes. So we can also say that equilibrium of force is simply a situation whereby the total force acting on the right hand side is equal to the total force acting on the left hand side. So I said we can also say that equilibrium is a state whereby the total force acting on the left hand side is equal to the total force acting on the right hand side. So I think the first sector of maths, let's still talk about rules of equilibrium. So if I know that, let's quickly move to moment. I want us to talk about all these things, then we'll now start to put it into practical use. So I said equilibrium of force can also be said to be a state where the total force acting on the left hand side is equal to the total force acting on the right hand side. Now please write for me moment of force. Moment of force. Moment of force. Please, how we are doing it, we are arranging it like that, because our goal is for you to pass the exam. So don't arrange it moment of force. Yes. Moment of force. Have you written that?
Yes, sir.
So you see that moment of force is the turning effect. Moment of force is the turning effect produced by a force. Moment of force is the turning effect produced by a force. Moment of force is the turning effect produced by a force. Moment of force is the turning effect produced by a force. See what I mean? If, for example, you go to on your tap, that tap that turns water for you, should you do it like this, is it not true? And that time you do it and it turns peacefully in your mind, that effect that you experience, that effect, that your force application and the effect produced as that thing rotates is what we call moment of force. Assuming you tried it and it refused to rotate, you will not have that water, should be? Yes. So that effect that storm gives you is what you call moment of force. So what I mean is, for example, if I know that I am applying force, let's say this is my force. So we need to look at it that anything that has to do with moment of force talks about y-axis. That's how I want you to see it now. Yes. Why everything that you normally have as your x-axis in this case means distance. And remember that x is considered distance. Are you aware? Have you noticed that sometimes they use x as distance? Now, in moment of force, whenever you're talking about moment of force, you are no longer having x-axis because there can never be any use for x-axis. As you move to top, you see the reason why. So whenever you're talking about moment of force, think that the force you are applying is the y-axis force, or you are applying that force vertically. As you place your hand on it, you are applying it. Then when you make that contact, it can go 360, it can go to any angle, no problem. But the first point of contact is that you are applying it directly to it. So you are taking it as a y-axis. If this thing rotates, however it rotates, it's not your business. But that turning effect that when you apply this force, it gives you, be it going 360, be it going to 90 degrees, be it going to 180, be it going to any angle, is what we call moment of force. But when you are not talking about moment of force at a point, that is where you are not considering that the turning effect should be only 90 degrees. Are you seeing it? So that one is what we call curve. So right. So moment of force is simply the turning effect produced by a force. One moment of force at a point is the force times perpendicular distance. Or you say force applied at 90 degrees. Am I too fast?
Yes.
Okay, I said I'm trying to put the two together so that as you are writing, you are comparing it to remember. This one is the turning effect produced by force. One moment of force at a point is the product of force and perpendicular distance. Or you can say that it is the force applied at 90 degrees. It is the force applied at 90 degrees. We've done equilibrium. We did equilibrium last year. But we're having to repeat it because we said that we are starting from the beginning. So I said this one. This with the turning effect of force can be at any angle. Why, when we are talking about moment of force at a point, we are giving it a limitation. moment of force at the moment, we're giving it a limitation. Now we say that this is simply the force times the perpendicular distance. So you say product of force and perpendicular distance. So you say force applied at 90 degrees. How many have we stated now? 3. 3, should be? Alright. You will start to see us putting everything that we're stating now together for use. But we want to see that, see to it that you understand that these things are actually easy. So that when we start using it, you see that it's not a problem. So number 4, rules of equilibrium. Rules of equilibrium. We have 1, we have 2, we have 3, we have 4, we have 5, we have 6. So rules of equilibrium. The first rule, there are so many of them, but we just know that all of it can be classified into just 2. So the first one is that the sum of upward force must be equal to the downward force. Rules of equilibrium. The first rule is that the sum of upward force must be equal to the sum of downward force. Full stop. The sum of upward force must be equal to the sum of downward force. Full stop. That is the total net force of a system must be equal to 0. So I said the sum of upward force must be equal to the sum of downward force. And I said that is the total net force must be equal to 0. That is the first rule. The first rule. The second rule, I will give you 3 rules. These 3 rules will help us solve any question or moment. So the second rule is that the sum of the clockwise moments must be equal to the sum of the anti-clockwise moments. The second rule, the sum of the clockwise moments must be equal to the anti-clockwise moments. The sum of the clockwise moments must be equal to the anti-clockwise moments. We know that clockwise is this way, is it not true? While anti-clockwise is this way, should be? So it's saying that the sum of clockwise moments must be equal to anti-clockwise moments. That is the total parallel or the total net parallel force must be equal to 0. Yes, because when you're talking about clockwise and anti-clockwise, you're talking about parallel forces. So that means the total net parallel forces must be equal to 0. That is, the total net parallel forces must be equal to 0. That is, the total net parallel forces must be equal to 0. Now, the number 3 and the last one. Number 3 and the last one. Number 3 and the last one. Notice that from definition, we talked about equilibrium of forces, talked about moment of forces, then we talked about torque. Now, notice that somewhere now, we've gotten something about equilibrium, upward and downward. Now, we are talking about clockwise moment and anti-clockwise moment. Now, the next thing you need to now know is that when you are not thinking of it, what of a situation where it's rotating at 90 degrees? So in that case, that is what gives us number 3. Number 3. So right, number 3. The sum of clockwise torque must be equal to the sum of anti-clockwise torque. The sum of clockwise torque, T-O-R-Q-U-E. The sum of clockwise torque must be equal to the sum of anti-clockwise torque. Yes. The sum of clockwise torque must be equal to the sum of anti-clockwise torque. And what that means is that, see what it means. We know that, we said that torque is the same as say force times perpendicular distance. You remember? So the one that is on the clockwise direction, the sum of it must be equal to the one that is in the anti-clockwise direction. So we need to note that. Which means that the total net torque must be equal to 0. We are noting it now. Now, please, under this torque, we are still under torque. Sorry, we are doing rules of equilibrium, should we? Yeah. We just finished the 3 rules of equilibrium now. So, please, before this number 5, let's say I call this one number 6 and this one number 7, because inside that torque, inside this equilibrium rule, let me call this one number 5. I want us to talk about couple and couple, work done by a couple, work done by a couple, and then torque of a couple. Yes. So that is it. 7 major topics. Yes. You see that this one still falls under this moment of force, but it's not bad if you just do it as a topic on its own. So first, so after rules of equilibrium, we are treating couple, shall So please write couple.
Sir,
Okay, ask.
sir, is there anything like sum of algebraic component of force as
Some
regards
of what?
algebraic component of force
Yes.
as regards to this equilibrium of forces, especially in this rule of equilibrium? Is there anything like that?
Yes. Now see some of algebraic components of forces. Notice that what I have here is just something I just showed out for you. This side is my anti-clockwise. Is it not true?
Yes, sir.
This side is my clockwise. Now notice that if I have this to be vertical, y-axis, I have this one to be horizontal, x-axis. Notice that this one because my upward force. This one because my downward force. Is it not true? Why this one because my parallel force? That is moment about clockwise axis and moment about anti-clockwise axis. So when somebody tells you some of the algebraic sum of the components of forces must be same. The person is simply telling you upward, downward, and then the anti-clockwise and clockwise moments. So we've been able to split it. So there's no need for diagram. Just have it in mind that what you're doing is first upward, downward, moment clockwise and anti-clockwise, third clockwise and anti-clockwise. Alright, so couple, right? Couple. A couple is defined. A couple is defined as forces whose magnitude are the same but of opposite direction. A couple can be defined as forces whose magnitude, you know that magnitude means values, is it not true? Are the same but of opposite direction. Another way to define couple is to say two forces with equal magnitude but opposite direction can be said to be couple. So I said a couple can be defined. A couple can be defined as forces whose magnitudes are equal but of opposite direction. See what I mean? See what that means? See what that means? Let's say we have a force here. And let's say somewhere I come and see that there is 2 newtons this side. And notice I come and have maybe, it's not every time it will be like this, but a situation where I have this kind of case, I come and have another 2 newtons, exactly 2 newtons here. Notice that what I now have in this case is what we call a couple. I can have a situation where maybe this thing is like, let's say 3 newtons. Automatically this is not a couple. But for the fact that I just come and see a question, the force this side is 2 newtons, the force this side is 2 newtons, is a couple. So once or let's say I have force this side, and let's say I have, let's say a mass on this, then I have another one, and I'm being told that I have force of 5 newtons this side, and I have force of 5 newtons this side. What I have is a couple. Are you seeing it? So once you notice that the forces are equal, but their directions are different, depending about the couple. Is important. So, but a situation maybe I have 15 newtons here, 5 newtons, and I don't have business with talking about couple here. So that leads us to the next one that says work done by a couple. But before work done by a couple, let's treat talk of a couple. I need you to know that talk of a couple is simply defined, right? Talk of a couple is defined as the product of force and perpendicular. No, I said before we treat work done by a couple. Let's do work done by a couple. Okay, so talk of a couple, shall we? Yes. So talk of a couple is defined as the product of force and perpendicular distance. Is defined as the product of force and perpendicular distance about each force found on a couple. I said talk of a couple is defined as the product of force and perpendicular distance, the product of force and perpendicular distance about each force found on a couple. The product of force and perpendicular distance about each force found on a couple. So what that means is that, for example, if I'm asked to find the torque of this couple, just this thing that I've drawn here, if I'm asked to find this, what I'll first of all check is what is the total distance of this particular rod. So let's say this rod now, is like, what measurement do you want? Let's say 6 meters. So I'll now ask myself, half of this 6 will be what? 3, should it? That means that this side to this side is having like 3. Why this side to this side is having like what? 3. So what the torque of this particular couple will simply be just giving me T equals, I will come and carry this in 2 Newton. Now this particular one is times 3. I say it, that is the torque for this one, for T1. Why this side for T2 will simply be equal to this 2 Newton, then times this 3. I say it. Now notice something, I want us to do something. 2 times 3 will give me what? And this will be 6 Newton meter. This is also going to be 6 Newton meter, is it not true? That is why we have an equation that we normally use for this. If I have 2Fr, I want us to do something. 2 times the force is here. How many forces do I have there? 2. Okay, 4. Now, 2 times 2, shall we? Then times 3. What do I have? 4. Is it 12? Yes. Now, when you add up these 6 and 6, what do you have totally? 12, shall we? Yes. So, we can also say that the torque of the couple is given by 2F. What? I should look at the table. Okay, it's blocking you. And you didn't talk since. Sorry. But it's not blocking these people. Wow. Alright, so see, I know it's not blocking anybody. Don't worry. Let me collect my duster. Alright, so see, I said if you check this, I've been able to establish something here. And I've been able to establish something here. Now, when you check it, you see that the total of couple here is 6. The total of couple here is 6. Now, when you put it together, the total torque here is going to be 12. And that means that torque can simply be given by 2Fr, where F stands for force and R stands for the radius. Not distance, R stands for the radius. So notice that once you are dealing with a torque, it's very important to consider the radius. Because if you say distance, notice that you might want to consider everything here, which is 6. Is it not true? And you have issues. You are asking your question. You don't understand. But first of all, I said I define torque of a couple as the product of force and perpendicular distance about each force found on a couple. So that's my definition. Now, and I said if that is the case, the torque of a couple here, this particular couple here, if you do it, you are saying that this is the force and this is this perpendicular distance, R. Notice that R here is the perpendicular distance because I'm moving from this end to this end for this particular one. Moving from this end to this particular end for this one. So if we do it and putting it together, the total torque will simply be everything I have here, which is Fr plus Fr. Now, Fr plus Fr will be what? 2Fr, shall we? So even if you don't want to memorize this formula, you can still solve it. When you finish solving it, you get the final answer correct. So what is important to know is that the equation for torque of a couple is given by this. 2Fr. Question of but if you don't want to cram this formula, I normally like situation where you don't even know the formula, so that you will always solve it on your own. Because sometimes if you start trying to memorize formula, you've limited yourself with so many things. But if you're able to know it, that you should be able to draw it and see what you're doing practically, it will help you. Alright, now let's move to work done by a couple. So my friend has cleared you, Chevy. So just know that once you hear torque, it has to do with something of force and distance. But when that torque has to do with couple, this distance gets replaced by R because couple involves two things that are the same. So if it's that case, the D now is no longer going to be D, but D divided by 2, which is R for this one, R for this one. Once it has to do with couple. So know that. Okay, so work done by a couple. Work done by a couple. Work done by a couple. We all know that work is given or is defined as the product of force and what? Displacement. Shall we? Not distance. I've noticed some students are very used to. If you ask them, they will say work equals to F times D. No, this is okay because we know that yes, sometimes we consider distance to be the same as displacement. But when we are treating work proper, you need to always think of this as displacement, not distance. So it's simply F times S. And we know that you can't say that work has been done if something does not move. Is it not true? And notice that since we are talking about work done by a couple, notice that that time we did this thing for third. Shebi is rotating 90 degrees, is it not true? And this one is also rotating 90 degrees, is it not true? So notice, if for example this thing is like your steering now, just please pay attention because I don't want us to rush into solving calculation without you understanding this thing properly. Now, if I try to move this way, it's going to be going to the right, Shebi? If I try to move this way, it's going to be going to the left. Now, when I'm on a straight load, I maintain balance, really tapping it little by little, Shebi? This kind of case is what we call couple. There is an effect on this force that when you apply it, there are equal forces, one for the right, one for the left. So notice that when you rotate fully at 360, you want to turn, is it not true? Yes. So you see that your turning of this and turning of this is giving you, if you check, slight circular motion. You move circular, but not fully. Is it not true? Yes. So that simply means that when I'm considering work done by this stuff, remember what work is. Motion must be involved. So the work done by a couple is such that what you have here is actually rotating. So that means that the S I'm going to be using when I'm considering couple is no longer just S, because this S naturally in linear motion we know is VT, is it not true? But when we did circular motion, for those of us that were not in our circular motion class, we said that S means descending as theta. Is it not true? And that anytime we are talking about cycles, the radius is constant. Shebi? So we put theta R to it. Is it not true? And we also say that theta is the same thing as 2 pi. Shebi? You still remember? Yes. Now let me break down this R. So I have this. Which means that work done by a couple is simply force times angle of rotation. So I can simply put this thing as the same thing as saying that work done by a couple is also the same thing as saying force times 2 pi r. Are we together? Obviously it's not confusing. Okay, but you know how I got this S? From work done now. And work done is simply force times displacement. So I'm not saying that in linear motion, S is just equal to VT. But once something has to do with rotating, that the S line is no longer going to be VT, but rather we put that our theta. I will not say that anything that involves rotation always comes with this constant arm. So replace the S with theta arm. And if you can replace theta arm, S with theta arm, this theta arm means the center is 2 pi. This one is in degree. This one is in radians. So we know very well that, for example, in secondary school, they told you that if you have a circle, for example, just remember that time, they told you that if this is 0, watch, they just see something. This side is 90, do you agree? This side is 180. This side is 270. This side is also 360. Just be watching something. So how many, if you remove 0 now, how many things do I have? 1, 2, 3, 4. You see not true? This side can be the same as say 1 over 4, 1 pi over 4. Is it not true? This side can be said to be 2 pi over what? 4. This side can be said to be 3 pi over 4. This side can be said to be 4 pi over 4. And this side can be said to be 5 pi over 4. This side can be said to be 6 pi over 4. Yes? And this side can be said to be 7 pi over 4. And this side can be said to be 8 pi over 4. Do you still remember this thing? No. You've seen it before? Hey! Jesus! Should I clean it? Yes. No, this thing is not my machine. That time you have your zero first man. First of all, remember that thing. This is the reason why we say that pi is equal to 180. Because first of all, I have 4 pi over 4 now. 4 divided by 4 is what? Pi. So remember that time in secondary school, they normally tell you that 360 is equal to 2 pi. This thing, remember? This is equal to 2 pi. So this thing, remember? It's from this thing. They are saying we have your 0, but take it as 0 means nothing. Now start from 90, which is this this one, move to 180, move to 270, move to 360. Now for each half of it, when I have 0, I'm now saying from 0 over 4 is the same as 0, is it not? Move to the next point, which is 1 over 4. Move to this one, which is 2 over 4. Using that 4 angles, 4 special angles. Now move to this part 3 over 4, move to this part 4 over 4. By the time you do it, you get to the last part, which is 8 pi over 4, which is 46. Now you see that if 2 go here, you have, or if 4 go here, you have what? 4 go here, you have what? 2 pi. So this is how you get it. So this thing now is important to us because you will now see that if that is the case, we've been able to get 2 pi for 360. Yes. So if 360 is 2 pi, you know that 360 degrees, 360, a circle is equal to 360. Is you know what you normally say? Yes. So if a circle is equal to 360, it means that n pi is the same as 2 pi. So I can replace this theta here with 2 pi. Write down my r, then my s equals to. So if I want to find my s to be in radians, I leave it as 2 pi r. If I want my s to be in degree, I leave it as theta r. So depending on what is given to me. Yes. So I can train now. We now understand it. So that is just what I did here. So that we got that work done by a couple. So just notice that work done by a couple, is equals to Fs. And because of the fact that it's rotating, we now say that it's the same thing as saying F theta r. Another way to put this thing, because we are talking about couple, you can say that this is the same thing as saying torque times angle of rotation. Alright, I can clean so that we can now do the next one. Can I clean? No. Okay. Let's try to be fast. Alright, so the next one is center of gravity. The center of gravity. So if you are done right, so that we will now start our calculation. Center of gravity. Center of gravity. Okay. So I can do it. Alright, so right, center of gravity. The center of gravity is the point acting, center of gravity of an object is the point acting at the center. So it's the point acting towards the center. Center of gravity is the point acting towards the center downwards. Center of gravity is defined as the point acting towards the center downwards on any object. Is the point acting towards the center downwards on any object found on Earth. Yes, it's the point acting towards the center downwards on any object found on Earth. Why did I put on Earth? I've never been to the moon. We've never been to the moon. And we know that yes, in the moon, the center of gravity there is lesser than that of the Earth. Are you aware? Yes. But it is believed generally that once you're talking about center of gravity of anything, even if the thing has no regular shape, but it tends, the center of gravity tends to look for the parts where it runs through it in the middle. It tends to cut across it. It's always looking for the parts where it disturbs it. So we say that it is the force due to gravity, or the force that tends to hold an object downwards, the face of the Earth. It is different from center of mass because center of mass, unlike center of gravity that looks for it downwards and the center of mass actually looks for the point of concentration. Yes, so that's the difference. So for center of mass, it is simply the point at which the object has the most concentration. So for center of mass, so the center of mass is the point. Center of mass is defined, but we say it's the point with the most concentration. Center of mass is the point with the most concentration. Center of mass is the point with the most concentration. So a point will come when we'll be doing center of mass of regular objects, irregular objects, and so on. That's what we'll be doing during the week. Center of gravity and center of mass. But for today, I just want us to briefly equilibrium, everything equilibrium, moment of force, rules of equilibrium, couple, one done by a couple. So that during the week, we'll now take center of gravity, center of mass of irregular objects. Yes, because if you check, you see that even on your textbooks, they didn't go deep in that center of mass, like calculations involving center of mass for irregular objects. But in your exam, you will see it. Yes. So we will take time to see that we do that irregular object center of mass and regular object center of mass. So that in your exam, when you see it, you do not look as if you do not see it in textbook, you do not see it in class. God forbid. Alright, so please, with that said, I want to believe we've been able to introduce all these things. We now know a little about this, shall we? And we know a little about this. We also know a little about this. Well, we know a little about this. We know a little about this, a little about this, a little about this. But before we start with the calculation, consider a situation where I have this. And a situation where I have something like this. Let's say I call this my N, and let's say I call this my K. If this happens to be an object, let's say I have an object here, let's say I have an object this side, and I am applying force somewhere, and they ask you, okay, let me do it this way. Yes. Now, if I ask you, what is the torque? What is the torque or the moment here, moment of this object down here? What would be your answer? N? Are you sure? N? So which one is your force? N. Which one is your distance? Okay, what of a situation where I have this? And I have N here, and I have K here, and they ask you, what is your moment? Or let's start with torque. What is your torque here? Sorry. What is your moment here? What is your moment here? What's your torque? Shall we see that you are not standing? Now see, there is no moment, there is no torque here. Do you know why? Notice that there is no how for me to have a force that will give me a turning effect here. I see it. So for that reason, I have no business with torque or moment here. So if I'm considering this kind of force, what I should simply be thinking of is that my dynamics, where I'm having forward force and backward force. Finish. And the backward force here should be my friction. The one that is pulling me should be my tension. Finish. So for us to always think of anything torque or moment related, there must be a force that should be acting vertically and then a distance. That is why I told you to always think of your y-axis as your what? Force when you are dealing with torque or moment. So which means that in this case, if I have an object here, let's say I have an object here, and let's say this is my N now, and let's say this is my K, and I ask you what is the torque, that is what is T here, what will be the torque here? Remember that Y is always vertical, is it not true? Is Y not always vertical? Yeah. Y is always vertical. So if I ask you what is the torque here, what will be your answer? Look well. Apply vector knowledge now. Use our vector knowledge now. That's why we give. So that means that I will simply say a situation where I'm taking this thing Here, Chevy?
Yes.
So I'm going to resolve any to this y-axis. And wait, watch. This angle is theta now, is it not there?
Yes.
Thank you. Yes, because once you are taking to the y-axis,
Sine.
is sine, is it not? So first of all, the y-axis here is n sine theta, and this is my force. Remember, I told you to always consider your force to be y-axis when you are dealing with torque. It's important. So if that be the case, remember that we consider this side to be our distance. Is it not true? Yes. Then, so let me say that k here now is my distance d. So if we remember what torque is, torque is force times distance. And remember that this one now stands for our y, and y here is simply n sine theta. Our d here is simply k. When you write it, you see that this is the same as n k sine theta. Yes, very important to note all these things. Once you are not following these concepts I'm giving you, when we start calculation, it will be hard for you. So you need to know how to view these things when as we are going. So once you're talking about moment or torque, your view for force should be that, okay, it is always the force that is starting from the vertical axis. Then the horizontal distance is, the x-axis is my distance. So if I ask you on the x-axis, notice that if I resolve this to x-axis, I have no business with x-axis. So that is the reason why work done by a torque. Sorry, that is the reason why torque can always have FD this way, or you always have FD sine theta. You will not have business with FD cos theta in this course when we are talking about torque. And that is the reason. Because if I'm talking about force is x, and when I put this into x, the force has no turning effect. So if my force is at x, and I already have this at x, is this case, which expresses no moment, no torque. Alright, so please, with that said, let's go. There's a question I posted on the group. I need us to look at question 1. You use the experience that you've gotten now to solve question 1 for me. You use all the knowledge you've gotten so far so good to solve the question 1 for me. If you look at this, there's this thing about courses that if you are learning it in your mind, nobody needs to tell you that this is the kind of question you will see in the exam. Are you aware? Yes, because it requires you really paying attention. But some of you, somebody will sleep like 2 days reading units and dimension. Eh? Yes. If you finish reading units and dimension, you see like 1 or 2 questions. Yes. So, but questions like this, simple harmonic motion, work, energy, and power, which you are coming to, you will definitely know that you will see a lot of questions under that. So, using the knowledge we've gotten so far so good, I want you to solve question 1 for me. Yes, check the group charts. Check the group chat. I posted a PDF there. So solve question 1 for me. I will go around and check. You've seen it, right? I don't contribute. Okay, copy from somebody. Are you in the group? My friends, are you on the group? Check the PDF. So, yes. So it's the same thing, just that I made a mistake and posted it twice. How are you now? My people. Are you going to practical or something? Okay, that means that is last class, just thoughts, no assignments. Yeah. Yes, so notice the first one just said a body of mass 6 kg is suspended by a string and pulled by a horizontal force of 14 Newton as shown in figure 4.1:5. Calculate the tension in the string if the body is in equilibrium. Notice that there's an angle, that particular string has an angle here, and they did not give us the angle. So after solving it, I noticed that the angle that should be there is 34 degrees. Why? How did I know? Because there's an answer given to us there that we should have 72 Newton. Yes, 72 Newton. So please don't say that the angle is not given. Use the angle 34 degrees as it is in the second part of that diagram and give us the answer. I'll go around and check. Please make sure you are doing something. as we are doing it, we are doing it together. You see that if we are taking time to do this class as if it's a reading class, and each day you go, you will be filled. You know that yes, you learn something. So make sure you're doing something. Try, bro. Okay, I've seen one answer, one correct answer. We can make use of our time because I know once it's 4, you will not even want to hear that you are the one that wasted the time. But let's do it together. Please see. The first diagram there is something that looks like this. You notice that anytime they talk about ceiling, they normally give you something of this nature. Then they say this is T. What did they give you here? What did they give you here? Okay, is that all? Okay, 60 Okay, 60
Yeah.
What about this one? Okay, well now let's check again. They also give us another diagram. Is it not true? So please, how you'll be doing this thing is if you get home, you try to look for similar examples as many as possible so that you can test if you learned it. So the M gave us something of this nature. Then here, we have 34 degrees. Okay. So see, I think the reason why I rush to put 60 is because I know that weight, anything acting downwards has weight which is equal to mg. Is it not true? Yeah. And I can use this to become like 9.8, which is approximately 10. So put my 6 to it, it becomes 6 times 10, which is equal to weight is equal to what? So this thing can mean the same thing as say 60 Newton. Since I noticed that everything here is in Newton. So okay. So I believe if we use now our principle, normal general principle, I can actually see that yes, this one is simple, but I would love to start with this, but let's do this. So that we move from here to this point. Okay, now so if I have this line downwards and 16 Newton, I have that right to have something up as well, that is 16 Newton. Is it true? Do you agree? Yes. However, if I have something here to be 40 Newton, hope you now have the right to have another one that is here that is 40. Somebody wants to ask me how come? Parallel lines. And you still remember that if this side is x, this side is minus x, this side is y, this side is minus y. So that's just what we're trying to use there. So if that be the case, which means that if I have, let's say, something like this here, should be? I should have the same thing here. Are you agreeing? Yes. Okay, agreeing. Let's say, see what I mean. When you go through people's book, you know that there's reason for us taking these things how we do it. So I have T here. So I have that right to also have T here. So that is just what I do. So if that be the case, that means that this thing simply falls, and you know that if I have this is the same as being here. So please, I want you to now do for me. Whenever we have triangle, we've done vectors now. So what do we do? Whenever we have this setup where everything is on x, on y, and x, what do we normally use? So it's simple. This one is simple. But look at the one I want us to look at. Okay, let's complete it. Pythagoras is simply r squared equals to. Shall we? So that r now becomes square both sides. Take the square root of both sides. So that this becomes square root of 40 square plus 60 square. But do it for me. Take the square root. What do you have? What? Okay, 0.11. Okay, well let's try to look at this one. Let's Let's be very careful, as careful as anything. Now, let's say apply the same principles. But this time around, remember that there's an angle here. So let's say I have my 6 here, 16 here. I have my 16 here. And let's say I have my 14 here. And let's say I have my 14 here. Okay. Now, at this point, I am told that there is an angle which is 34 degrees. So, if that angle is there, that means alternate angles, I taught you yesterday, there's 34 degrees. Do you agree?
Yes.
That means I will remember that any angle this side is 90, which means 90 minus 34. What I will have here again is what? 6 degrees. Okay. So now, since I've gotten something that makes contact with the horizontal, now remember, please remember. Do you remember that this side is 60, Shelly? Yeah. That means what I have is also 60. What I have is also 60. Some of you don't know how to do this thing, but you will be saying after this, I will learn it. Learn it now. Alright. So let me just carry the one that makes contact with the horizontal and come out. So I will have 60. I have this. I have this. There are so many ways to do this. I could have said, okay, project T to this side, project T. Isn't always, but let's try to use SOHCAHTOA first. I will act normal. If you notice, I normally like using the ones that are normal to solve it first. But let's act normal first. Okay, that means the angle here should be what? Okay, somebody wants to ask me, what about this angle? Why didn't you break it? Remember that this angle is also here, should it? So I'll pull it out. This is the one I need. The one that makes contact with the horizontal. So at this point, I can start doing, okay, I remember that here, we named here T, should it? So this side is also T. But let's check. If that be the case, and T is what I'm looking for, I will now employ my SOHCAHTOA. So SOHCAHTOA. No need for 12 because tan is always sign with course. So this is opposite over hyper, Sin theta. Because the opposite over hyper, which is essentially as my opposite here, looking at this angle. The side facing the angle is always the opposite. While the side the angle is sitting on top is always the okay. So this is 6. My opponent is here is what? Well, let's check if cos will work. Cos is adjacent over hyper, and my adjacent is going to be 40 over what? Over T. Right? Okay. So let's solve for sin theta. I have trying to make this subject on the phone. I'm going to have what? Sin theta, and that is sin 56 degrees is equals to 60 over T, which means that if and anything standing on this one is over 1. Okay. If I do it, it's going to be T sine 56 degrees equals to 60. So we can divide both sides by sine. So that T now becomes equals to punch for me. 60 over sine 56. 70. 72.3. And 72.37. Okay, which is approximately 72, Jamie? Yeah. It's close, okay. So, and you know that this is going to be in little because that's the unit given to us. Okay, now let me go and put it. First of all, okay, now we brought down something about cos as well. And we said that cos is going to be 40 over T. Okay, but I need to check if I have use for that my cos. First of all, let's check. I want us to check something. Remember that cos is going towards the angle, Shelly? Yes. If I'm going towards this angle, yeah, we have use for it. It's up to us to now know what we need. We have use for it. So let's try to do for the cos and see what we have. So cos theta equals to cos and theta here is 56 all over T. So T cos 56 degrees equals to 40 Divide both sides by 4 is 56 degrees. Let's see what we have, please. 70 by 5, 3. So approximately 72 as well, Shelly? Okay, approximately 72. Alright, so please, whichever way you use, but I think the reason why I made the adjustment is because it's not everybody that understands this concept that we use here first. So that's why I made the adjustment. So please, it's important that as we are learning all these things now, you are seeing how to solve vectors. Okay, ask.
What's the point of finding the 60-degree right versus
What's the point of?
Still finding the 60-degree right versus 34.
Which 60 degrees? Huh? Which 60? The point of finding. I can't be here.
The point of finding the 56 degree.
The point of finding the 56. When we already have 34. Yeah. Okay, and you gave me the same answer. Yes, that's because you understand the concept of putting your sign and cos well. Yes, but you see that it's not everybody that understands that concept. Why we do that is because once we make angle with the horizontal, we always have that x is equal to cos theta. Y is what? Sin theta. We've done it before now, so that's why I did it. Since I have 34, get my 90, the other side is 90 now. Is it not good? So why I find out 56 is to put you back. Like there's something called habits. So we need to be in that habit that for x to be always equals to cos theta and y to be always equals to sin theta. Always make contacts. Always, whatever angle you are giving, if that angle is not with the horizontal, maybe they give you with the vertical, go and find a way to get the angle to be with the horizontal. Make it a habit. So since I have this to be 34, I get that my horizontal. That's my business. So, but if this one is penny, you use the one you know. You know that Jesus came for people that don't know. See now, so I believe when I'm teaching, I'm really for people that don't understand the matter. That's why in that question, when I saw this thing, I went there to make provision for this, so that we can learn the two. Is it which one? Okay, go to the diagram. Okay, well, see what we are doing. What we are doing is that there is a rule. There is a rule, even when we do parallelogram and triangular law, that says that if I have anything this side, that provided I'm not giving for this side, I should consider it to be equal. But that they are parallel. And parallel forces, once the forces are parallel, they are equal. You can even get it from your x and components, as you normally say this side be x, this side be minus x. So that's just what we did. If we know that there is 60 Newton acting downwards this way, that this line, there is also a, but naturally when you have that your rule or equilibrium, where we said some of downward and upward forces are equal. Is it not true? But this case, they did not give us anything upward, which means that since this is going downward, there should be an equal force upward as well. Yes. So that is what we did here. Stretch it. So when we stretch this one, we did the same thing. And some of clockwise moments to be equal to anti-clockwise moment. This still remember. So since I have this thing down this way, I should have an equal of it this way as well. So here I am as English. That is why, for example, let's say I have this right hand side. Now let's say I take it to be 40. Let's say this side I have it to be minus 40 as well. Let's say it's equals to 0. If this can cross equality sign, is that this because 40 equals to 40? Is it not true? This one means anti-clockwise, this one means clockwise. So it's important to know it. So clockwise side. So that's the same principle we use, but just that we're not putting it in place. We after balancing, we can get our resultants. Okay. Now, please let's go again because I noticed that I think this our method today is working. People are really working hard. But ask. Alright, yeah, another one. Which one? This one? The angle. How I got the angle? Resolve it. How I did this in there? Okay, I need somebody to go and explain it. But see, should we know that if this side becomes 60, Because this side is 60, is it not true? Which means that every line this way is also 60. And every line this way is also 60. So if that be the case, I use alternate angles. Alternate angles, if I have something like this, let's say I have this, I have this. Watch, the angle here is equal to the angle here. And the angle here is equal to the angle here. And if you still stretch this, let's say I stretch it down here. Notice that the same thing I have here, are you seeing this angle now? Is it not the same thing with what is running here? So that's the principle we are using. I have an angle. If somebody said I don't understand. I'm not supposed to be doing this, Shebi, you know. We've passed this one, this level we've passed it. But I want us to really pay attention. Let's do it once and for all. So that we don't go inside the exam hall and become handicaps. I see. I have, and up here I am given that this is 34 degrees. That's what it means. In fact, anytime you see any line or any stop at any point, even if they do not put it, always consider that every line you see, be it at an angle, is always rotating on that vertical and horizontal axis. So if I know that, and at this point they come and give me 34 degrees. What it means is that if, for example, I project this down to this one, let's say I have this again now, see. This particular end that I'm seeing is this. The alternation will be in such a way that it is crossing. So what I have here should go in. Are you seeing it? So if I know that, I now use my principle of 90 degrees to balance it out. So I have 34 degrees here. So what alternation means is simply, how do you, if I have this here, I should have something like this way. So you are reversing, repeating. While if it talks about corresponding, is simply that particular angle in another place, how can I find it? That is why that time we normally do something like this. We say that this thing is the same as something like this. So I believe if this thing is still confusing you, what you just need to do is to message me, so that I will do a class, video class on circle theory, angles, and polygons, and send for you the YouTube channel so you can watch. Please start solving the B part of this question. Start solving the B part of the question. Yes. The B part of the question, that's our PDF. Make sure you are doing something. Make sure you are doing something. Make sure you are doing something. When others are solving, be solving. And others are solving, be solving. Please, get out yourself. Please, yes, we are going to be dismissing by 3:30. Once we dismiss, switch class students will stay back. We are dismissing by 3:30. Even if we dismiss by 4, once we dismiss, switch class students stay back. Yes. Did you hear me? Yes. Even if we dismiss today by 5, even if we dismiss today by 5, switch class students stay back. We must dismiss by 4. I said 3:30 as play. Because we have a pause. We can't dismiss anything other than 4. So the B part says something about moment. A uniform, yes, the B and the BII part. The part that says define moment of force and then a uniform shaping. Make sure you are doing something, please. Be happy and be doing something. Before you leave your one, I should know all your names. Yes. Somebody said, is it possible? That one, you will see. Before you leave your one, I ought to know all your names. I read the question. Please pay attention. Read the question. Let's start from the beginning. Read out the question. Read now. Well, you have solved to the point where you no longer know how to read questions. Read now.
Of mass is equal to
I know that the words that we ask on this will be that one, is it not? And 50, that is what is equal to 10 G now. So 50 times 10 is what? Okay. One again, I am.
Suspended horizontal by 2 wires.
By 2 wires.
Attached at 20 cm and 90 cm.
Okay, let's say this is 20 cm.
Yeah.
And then 90 cm, eh?
And 90 cm respectively from the end. From the ends of the road.
Okay, that means, hope you know that meter for the uniform meter or 0, that the full measurement should be 100 cm.
Yes. But this one is more than that.
Okay, that means that this is actually the 100 cm. That means that 10 is off already.
Yeah.
Okay, then I have here 20 off already. Because everything here runs from 0 to 20. Okay. Okay, again, that means they say that there is wire attached here. I know that if you attach wire to something for it to have balance, the first acting there is the tension. So do you agree? And it's acting upwards. Okay.
Calculate the tension to each wire.
Okay, this tension is what we are calculating. Or Google? Okay, well, let's start, please. Please pay attention to this. Pay attention to this. The first thing I want you to always think of is our principle of moment and that of equilibrium. Remember in equilibrium we have that sum of upward forces must be equal to sum of downward forces. Is it not true? Which means that here I have T1 plus T2. Is it not true? Equals to 500 Newton. Is it not true? So that means that upward and downward will go to, which means that if I make T1 certain of something like here, I should have T1 equals to 500 minus T2. Is it not true? Question 1. Okay. So we didn't make someone run the 6, alright? Yes. Okay. So please see now. See, let's now check something. If I am going to be finding, I've already gotten T1, but I don't know what T2 is because the minute I get T2, I'll be able to put T2's value here and get my T1. Is it not true? Yes, I see it's done it. Well, let's check. The total measurement here, what is it?
70.
What's the total measurement? 70. You know why I'm telling you to find that total measurement? Because I've already, you will always get T1. Or you will always get any one. Let's say it's T2 and let's set it up the formula here. When I get it, I'm not trying to make T1. But since I've gotten T1, I'm not trying to find T2. So I will imagine it that I'm pointing the whole force now towards this side. This is the first approach. But please, when you are at home, try this in different angles. Try it in different angles, such that you are using brick by brick. But please, this is a method that always works. So when we try this, we try using our second method. Alright, so if I'm pointing the whole force here towards this side, let's check. Let's point all the forces we have this way, down to T1. What am I going to be having? And I have that T2 will be equal to, remember torque, what torque is. So what it means is that I'm finding first of all the equilibrium of forces, the sum of forces up and downwards. That's what I found first. Number 2, what I'm finding in this, using this method is that I'm finding the torque. So I'm finding the torque. Sum of torques should be equal to 0. Remember that torque means when it's rotating. So I'm not checking. This thing now that I have here is T2. And T2 is simply the same thing as saying T2 times, the torque of T2 is simply T2 times its perpendicular distance. Do you remember? So that means T2 and its perpendicular distance, which is 70 and T2. So I'll write it. So in this case, I'm finding the torque. So I have T2 times 70 shading. Okay. Then is equals to, I'm checking again, is equals to, I can say minus, what we going to use it for minus? So that by the time you cross the equality sign, they are equal. So minus, what I have here, the next force I have here is 500. Is it not true? Yeah. So I have 500. The top of this 500, if I have this 500 down, 500. The top of this 500, the distance here is going to be what? Remember that this point is the center point, is it not? 50. So 50 to 20 is what? So times 30. Is there anything to minus again? Is there anything to minus again? Somebody might imagine, when we start using our second method, we will imagine certain things so that you see that it will still work. See, the reason why I'm not going to be doing T1 times, because there's 20 here already, is it not true? The reason I'm not doing T1 times 20 is first, I've made a solid of formula. Second, it is my fulcrum, it is my balance points. So when I have that balance, I have no reason doing this way. So everything here should be equal to 0. So first, I get my equilibrium. Second, I get my torque. 3. This equilibrium is the same thing as my moments. Check, because anti-clockwise and clockwise here. There is no use for that, so I did not get clockwise and anti-clockwise moments. Yes, so I should be correct. All right. So at this point, before my stage 3, do for me. Okay, this is the same thing as saying 70 T2 is equals to 500 times 30 is what? 15,000. Please, we are going to exhaust all the methods available for this kind of process so that we know it. Alright, so if I have 70 T2, then equals to 15,000. That is this thing cross the equality sign, minus sign. So divide both sides by 70, let's see what you have. You got C2 to do what? 214.28. Is it good?
Yes.
Okay, 29. Yeah. Okay, which is in Newton, Chevy? Okay. That means that I can go back to my T1 and say that T1 is actually equals to 500 minus 214.29. What is the formula? Let me see what you have. 2 days. Oh, how many calculators? 285.71. And it's going to be in Newton, Chevy? Yes. We are configuring this first method. Copiando. Okay. I'm coming. Please pay attention. See, pay attention. All those things you want as let me claim this. No. See, I have. Just pay attention and I'll take it gradually. Take it gradually. Do you know one thing about this thing is that once you learn it, you plant it. So I have the 20 centimeter mark. Then I have 90 centimeter mark. Somebody wants to ask me, how are you getting this thing? They said that there is wire attached to it at 20 centimeter mark from both ends. So let's say this wire has tension. Anytime you have strength or wire, this one is T2 for the second wire. Now, I know this, and let's say there is 50 kg mass applied to this. 50 kg. Now, please, the approach you want to use is method 2, the one I used at home, to get that answer I put beside it. Now, if I have this, this should be 50 times 10, which is going to give us 500 units. 500 units. So what I'm going to be doing in this case is simply to get T1, point everything to all the forces towards this side. To get T2, point all the forces towards this side. Are you seeing it? Yes, if you don't want to stress about it. Notice that the first one we did, we applied the rules of equilibrium, getting upward force, getting downward force, then getting torque. So now let's say I choose to do that using that principle now. I'm pointing all the forces this way. Guys, to get T1 now, point all the forces this way. To get T2, point all the forces this way. Are you seeing? So that if I'm in T1, this is what is giving it its balance. While if I'm in T2, this is what is giving it its balance. So if I know that, I will now say the total distance from this point to this point is what? People that will ask me, how did you get 70? I'm not paying attention now. But immediately we finish, they'll ask me, sir, how did you get that 70? The total distance from T1 to T2, which is the support. Remember, it's T1 we are getting. I said, point everything this way, point everything this way. If I'm getting T1, point everything this way, point getting T2, point everything. Yes. So I will now have that this is going to be the something I say T1. That is the top of T1. So what I'm using in this case is just the top. The top of T1 will simply be T1, and the total distance from T1 to T2 is what? 70. Is it not true? So times 70. So then I will have minus. Why am I using minus? I'm using minus to show that it's equal, or you can just say equals to. Now the next force that is pointing to this T2 is this one. Is it not true? Yes. So it's equals to 500 Newton. Then what is the distance from this point to this particular one? 40 times 40. I see it. So that I have 70 T1. Is it was 500 times 40? 20,000. Okay, we will divide both sides by 70 to make it equal 7 on the formula. So T1 now becomes what? 0.7 should be in Newton. Is it not? Alright, so I've gotten T1. Now if I want to do T2, do the same thing. I see it. So if you don't want to be stressing yourself doing this equation 1, equation 2, just employ the formula of saying if I have two forces or two tensions, if I want to get whatever tension is there, point all the tension to the other one, that's is balance. Point the other one to the other side, is balance. You get the same answer.
But this one is nice in the last.
No, it's not. This one, it's not that we're able to get the upward and downward force. Couldn't have gotten it now. Yes. So this one now is simple. This one is simply, this is the one I used at home. This one now, see what we are doing here. This one we have to employ all the equations of equilibrium, up and downward first, before top. But if we know that simply we can just point everything here to its balance. Point everything here to its balance. So it's not, we have questions. What you're saying is that you see, please, hope you remember what we mean by you. See, do you remember the reason why we didn't put T2 in this question is that we are taking it that if we are pointing everything here, we are pointing it to its balance. When we want to find T2 now, we are taking it that this one now becomes its balance, which is this way. So if we are doing that, when we are pointing towards this part, we are not making use of this. And when we are pointing this one towards this part, we are not making use of this. So that's just the basic. So the thing is just the same thing with that time I taught you equilibrium of forces. If you remember, that time I told you that if you have a pivot here, and let's say you have something like a force here, F1, and let's say you have something like F2 now, we now say point the force, which one is going anti-clockwise and which one is going clockwise. Are you seeing it? So we normally point to this one, point to this one. So that's what we are doing. So in this case, if we are putting it, then this one goes in. When we are doing this, you notice that we don't ever check, we don't come and say what force is here when we are doing this thing, rather than distance. So that's just what we are doing here. Point this to this, point this to this. Okay, so please, with that said, I want you to copy. I want you to copy me first. What's the time? We have to finish the 5 questions there. We are the one that delayed us now. Are you not the one that delayed us? Wait, but this going home that you people like rushing to go. What do you people do at home? If I buy food instead, you did not say it on a weekday. I'm going to tell them weekend. Yeah, my friend. Shebi? Okay, Tuesday. That's it. You know, Tuesday is morning, and if people agree to stay on it till 4. We'll do it. Okay.
As long as you come in the cooler.
So as long as I come with cooler.
Yes, and drink cold water.
So please, let's solve this one together, the next one together. Then we go. Let's solve the next one. The one that says a wooden platform is suspended from the roof of a house by ropes attached to its ends. Yes, a 5-meter wooden platform is suspended from the roof of a house by ropes attached to its end. Yes. Then the carpenter weighing 800 meters stands 1.5 meters from the left end of the platform. Yes. If the weight of the platform is 150 meters, yes. So please, let's do that one together. Can I do it? Please read the question. Let's read one small.
Suspended from the roof of the house.
The 5-meter here.
Suspended from the roof of a house. Roof attached to the end.
Okay, rope attached to its ends.
Yes.
Okay.
The carpenter waiting.
Once you hear rope attached to any point, know that there will be tension on that rope. Okay.
800 meters.
The carpenter, eh?
800 meters.
Okay.
Stand 800 meters.
Okay. This guy, eh?
Stand 1.5 meters from the left.
This is 1.5 meter.
Left end of the platform.
Okay.
If the weight of the platform is 150, calculate the tension of each of you.
Okay. If the weight of the platform is 150 Newton, and you know that we said something about center of gravity acting towards the center, is it not true? So that means I can take it that in between this we have our 150 Newton. Okay, check if there's any other activity towards the gravity. Okay. So first of all, remember that everything here is what? 5 meters, shall we? That means if everything here is 5 meters, that means that the distance from here to here now is now 1, shall we? Remember, we are not using measurement to do this thing, but let me open this way so that we don't confuse ourselves. 1.5 meters. Automatically here becomes 1 meter. So we can still use the same approach we used for the last one to solve this question. Everything here is what? Is it not good? Okay, well let's use the first method we use, then we'll use the second method and see. So we will do upward force. Why I normally use that first method is for you to remember the rules of equilibrium. Upward force must be equal to downward force. Clockwise moment equals to anti-clockwise moment. Clockwise stop must be equal to anti-clockwise stop. Or some of torque must be equal to. So let's do upward force here is what? C1 plus C2 shall is equals to 800 L plus 150. Now please, do you remember that actually the weight, if I hold this thing, there's a weight on this thing downwards, shall we? Yes. This object has its own weight. That's that 150 that they are talking about here. Shall we, you know? But if I keep something on top of this thing and it exerts weight on it, if there is no balance, definitely it will cause it to change, shall we? You need to pay attention to that. So that means, first of all, we get that T1 plus T2 will be equals to 950 Newton. So which means that T1 can also be equals to 950. So equation 1. Okay, I'm happy something. So once they see this equation 1, we're taking that is not for them again. Okay, yes. Now the next thing, remember that this part is when we do equilibrium. This method 1 is us first finding equilibrium. Then we find torque. Then we use equation 1 and equation 2. So the second part is where we find our torque. And we know what torque is. Torque is simply force times distance. Force times distance. Force times distance must be equal to force times distance of distance. That is clockwise torque must be equal to clockwise torque. Alright, now let's check. If I have this T1 that is here, notice this is T1. If I'm pointing this T1 now, watch and pay attention. If I'm pointing this T1 that I have here, then I attach to both ends. So if I'm pointing this T1 towards this T2, what do I have? Is it 5?
Yes.
Check. Remember that there is weight here. Is it up to you? Okay, that means that I will have T1 times 5, should be?
Yes.
I'm pointing to this. Is it not to? So minus or is equals to 800. Am I right? Alright. See, let's do it this way. Let's do it this way. This is C1, this is C2, shall we? Stop. The last C1 times. How about this is 2.5? Yes, ready? Yes. Minus T2 times 2.5. 2.5 times 2.5 is that 5? Is it not good? Yes. Alright, notice something. Do you know why I put minus here? The reason is that notice that this thing, remember that torque is clockwise moment against anti-clockwise moment. Yes. That clockwise torque against anti-clockwise torque, which means that if this one is going this way, this one should be going this way. And when you put it out, there should be equal. That's what I mean. Okay, so everything here. Now we need to check. This is clockwise torque, clockwise torque. Now we need to equal this to 0 plus. Someone wants to ask me how. Remember that there is force here as well. There is force here as well. Or let's do it this way. Minus. Yes, so that you don't get confused. Minus 800 Newton. Minus 800 Newton equals to 0. We are trying to get all the force now. And notice that this 800 Newton is having 1. 1 times 800 is 800. The distance, remember what torque is now? Torque is simply force times distance. So what I'm doing is I come to T1. I come to T1. Assuming, see, relax, it's not a joke. Assuming, keep quiet now. See, assuming I wanted to point everything to this part, I will not have this for T2. But we are not making it that, okay, if you want to carry everything along so that you see what we are talking about, that is sum of everything torque should be equal to 0. We are not saying bring T1. What is this distance? It's part of this, which is 2.5. Bring T2. What is this distance? 2.5. We have it here. Then what again is here? The forces, all the forces, we are getting all the forces at this distance. So we have 800 Newton, then times 1. Which will give me 800. Now, somebody wants to ask me what of 150? Remember that 150 is actually the weight of this object. Is it not true? Yes. So it has no torque. It has no torque. That particular weight on it, in as much as it's acting outwards, but it's the weight on this, it has no torque, no distance for it. Okay. So that is why I have this. So when you put this thing out now, we can still do the mathematics there. So when I did it this way, so that you don't see reason to be confused. So once we are done with this, we use our method 2. Like you see that it's the same thing. Let's finish this now. Alright, so this now because the same thing I'm saying 2.5 T1 minus 2.5 T2 minus 800 Newton equals to 0. Just that's why I gave you those rules when we started. Because once you're obeying those rules, no issue. So whichever one we want to use it, we will always get an answer. What we are doing this. So this time because the sentence is saying 2.5 is common to these two. Is it not true? Like I said, 2.5 into T1 minus T2. Hope you agree. Yes. So give me the sentence. So minus 800 Newton equals 0. This one can cross over equality sign. So that I now have 2.5 T1 minus T2 is equals to 800. So divide both sides by 2.5. So that this will get out. But do for me. 800 divided by 2.5. 320. Okay. And we know that somewhere we've gotten T1 to what? 950. Okay, which means that this can be decided as saying 950 minus T2 minus T2. Is it not true? Everything here for T1 is equals to 320. Alright, minus is going to give me 950 minus 2T2. Is it not true? What's the 320? Okay. This can cross over so that I have
950 minus
7? Yes.
20.
What do you have? Yes, okay. It's equals to 2T2. Divide both sides by 315. Shall we? For my T2. Okay. That means that I can go back to T1. Yes, that means I can go back to T1 now to say T1 is equals to 950 Newton minus 315. What do you have? 635 in Newton, shall we? But let's try to use our second method to see if we can get the same thing. See, even this first method and that second method, they are the same thing. If you look at it very well, you observe that it's the same thing. So once you've learned that particular method, it's the same. Shebi, that your second method will work for you. So it's the same thing. No, he knows that second method. Yes. So whichever one you use, you still get the same answer. Okay, I will analyze.
Have two options.
Let's check. I like your spirit. That's the spirit of a big man. That guy is a big man. So just look at him and remember when I said that he's a big man. He has this Coscharis. How many of you have heard of Coscharis before? Coscharis Motors. That guy is like him. Yes. He insists on things till he gets it. Oh yeah, let's go. Please, I want to play so we use method 2 and check. Can I claim? If you say we should wait, we wait too, but we must do it. So even if it's by 5.
It's already 4.
So please, I want us to, by the time we learn all these things and finish, I want you to stick to method 2. Shall you see that this one is stressful? You do equation 1, then come and do equation 2. You are even making room for certain things. Okay. Alright, so please, let's use method 2 and stick to it. Once you have stop. What you use in physics is the man. You know that physics is physical things. Physics is not just about numbers. What you are trying to do in physics, you have to do certain thought into it. Yes. So the only thing you have in physics is what we call manual work, breaking it down. But not like you are doing asaba. Asaba is 2 lines now. Where I can tell you, for example, I can tell you that any number you have, that by the time you add it and subtract, it will always give you 9. Do you agree?
Yes.
Shebi, you know? No, relax. So that's as up for you. So you see that mathematics has so many shortcuts. Yes, so please, if I know that somebody said earlier that he's not solving the question that is the problem, that is analyzing the question that is the problem.
Yes.
But the truth is that a way there may level one. Yes. Once you analyze the question finish, it will not be solving the question that is the problem. Now see. I have, please pay attention. I have my T1. I have my T2 because they say that they attach this thing to the ends. And I say that anything that has to do with rope or strength comes with tension. Now they told me that this particular block of mass has 150 Newton. Is it not true?
Yes, sir.
So if it has 150 Newton, we are using our manual method, which is our method 2 now. Now they said that there is 800 Newton by the man. Is it not true? After, from this point, 1.5 meter. That's what we have. Which means that if that is the case, that this everything here, the total length of this is 5 meters. Which means that what I have to this point becomes 1. That means I'm left here with 2.5. Is this all? Yes. That's all of the question, right? Yeah. So using our method 2, simply let's say we want to find T2 or T1. I make this my fulcrum. That means T1 will not be part of my business here. My business is with all the forces in this question. Yeah. So in this case, what we are using is this method is all about torque. So all the forces and its distance, with the exception of T1 and its own distance. So I will say T2, come here. I see that T2 is this way. Now, what is the distance of T2 to T1? 5, Shebi? So T2 times 5. We'll go again. We'll be using minus to separate the forces because we know that once you do minus, cross the equality sign, because the force. So minus. What is the next force there? You see that this method is so simple that you're not neglecting anything. You just try this now. So this is 150. Now, what is the distance from 150 to T1? 2.5. Times 2.5. Okay. Minus. This is the next force, Shebi? Yes. 800. What is the distance from 800 to T1? Times 1.5 equals to 0. Make everybody the equal answer. You still see somebody somewhere saying that they don't understand. Now, this is now going to be 5T2. Is it not true? 150 times 2.5. Somebody says
375.
Hey! Yeah, my village people. Minus 375, okay. Minus 1,200. Is it equal to 0, right? Yes. What do you for me? Minus 375 minus 1, 2.
1,500.
Shebi? If this one cross the equality sign, 1,532 equals to 1,575. Shebi? Divide both sides by 5. So this is going to give us 350, Shebi? In Newton. You see what we got to the other one? Yes. So you see that this our second method is actually the easiest. Yes. So I want you to stick to the method of 2, which is our torque method. Torque method. So we are no longer using that equilibrium principle, the first one up and downward before doing torque. Because we have to overlook something. But here, what it does is to say, using your torque, make one of the forces your fulcrum. Point everything towards that force, neglecting that force. If I want to get T1 now, what I will simply do is I will remove this fulcrum, take it to this point. That means I have no business with T2 when I'm finding T1. Which means all my forces from here, I point into this. Because my balance. So once you're able to always do that, you always get the same answer. So please, this is where we'll stop for today, but let's find T1. Let's find T1. You must learn. Yes. Alright, so if I'm finding T1, So this is now going to be T1 pointed this way. Distance from T1, this is my T1 to T2 is 5. So times 5. I still do minus again. The reason for minus is because once I put minus in the cross equality sign, it will show that this side is equal to this. Okay. Minus. What's the next force there? 800. Now, what is the distance from 800 to this T2? No, see that before. 3.5 should be? Yes. You sure? Minus. The next force is 150 should be? Now, what's the distance from 150 to 2.5? Is it not? Yes. Is there any other force? No. Equals to 0. We will do for me 800 times 3.5. What do you have?
8 minus 2,000.
Minus 2,800. Yes. Okay. 375. Like this. Okay, equals to 0. Okay. Now, minus 2,8 minus 375. What's it? Minus 10. Like this. Okay, so I have 5T1 minus 3175. Is equals to what? 0. Okay, so that I now have 5T1 is equals to 3175. So divide both sides by 5. What do you have? 635. Is it the same answer we got? Yeah. Alright. So please stick to this. And do you know how you know that you are correct? Is simply, since you have two tensions, you are supposed to, you can't be looking for two things in a particular question at the same time. Is it not true? Yes. So that's the approach. So please stick to this. So you can use the method 1, you can use the method 2, but I want you to be sticking to this. So with that said, go home, read, revise, eat. Always eat before reading. I tell my students, the secret to success is not just reading. If you don't have fuel in your system, you will not succeed. Yes. You need to be saying well. Yes. So it's not if you eat Ghana and drink, you say you've eaten up and you just finished eating now. It's a lie. You need fufu, serious eba, strong rice, beans, plantain, yam, all these strong food, not mineral and bread, cake and gala, meat pie, those things are not food. Few minutes, just it will leave you. So please, eat strong foods and it will fuel you up. So please, let us pray. And the next time we are seeing is on Tuesday, shall we? But have it in mind that, let me just tell you. No, Tuesday, which is Wednesday? Please, no, how we are doing our Tuesday class now is you have to come very early. So that in the hobby, we'll do our class immediately after Mass. Yes, in the morning, because there is no lecture. Lecturers don't come straight Tuesdays. So once we do our class in the morning, towards afternoon, you can go for your practical class. Please, once we dismiss, switch class students, stay back. Yes, switch class students, stay back. Somebody should pray for us. Somebody should pray for us.